Good morning. We're going to finish up our section 4.3 notes today. So we are on example 3, which is our first word problem using this natural base of e. But it's pretty straightforward and it's the same as what we've already done basically. So we have this situation that says the length L in centimeters of a tiger shark can be modeled by the function L equals 337 minus 276 e to the negative 0.178 t, where t is the shark's age in years. We want to graph the model and use that graph to estimate the length of a tiger shark that is 3 years old. So we're going to start by making our table of values. So in your y equals, you'll type in this equation, 337 minus 276 times, and remember e is right below the pi button, raised to the negative 0.178x. We just put x into our calculator instead of t. So in the table, remember, you don't want to start anything lower than 0 because it doesn't make sense to have negative numbers here. So at 0, we're at 61, 1, we're at 106, at 2, we're at 143.67, at 3, we're at 175.19, 4, we're at 201.58. Actually, let's just graph our even ones because that's what I have on my coordinates. So we'll do 0, 2, 4, 6, 8, 10, 143.67, 201.58, 242.14, 8, it would be 270.55. And at 10, we're at 290.46. Okay, so really quick, let's remember x is the age of the shark. And that's in years. And then our y is the length of the shark. And that's in centimeters. So at 0, so when a shark is first born basically, we're saying it should be 61 centimeters. Sorry about there. At 2 years old, it's 144, we could say. Right about there. At 4 years old, we're at like 200, just above it. At 6 years old, we're at 242. At 8 years old, we're at 270. And at 10 years old, we're at 290. So hopefully you can see this is going down, right? It's kind of curved this way, which makes sense. You should have the most growth when you're young. If we wanted to estimate 3 years, which we actually could see in our table, but we can estimate it from the graph too. Whoops, it's 1 year. So 3 years. Be right about here. So it looks like it's right about at 175. So at 3 years old, the shark is approximately 175 centimeters. So that's that first problem, and that's not any particular function. The next one gets into a well-known function. This is that continuously compounded interest. So that example that I went through when I first explained E on Monday, where I was talking about the Bernoulli brothers and then what Euler did, this is that equation where if we continually gave interest, so if you remember on Monday, we looked at, okay, what if you have 100% interest every year, and then we matched our R and our T, and we just kept increasing those, and we found that you get more and more money. So that's this idea of continuously compounded interest. You get more in general for this continually compounded interest. And this equation is A equals P ERT. So really quick, let's piece this apart. P is your initial amount. Remember, E is just a number, R is our rate, and T is our time. They call P the principal, but that's the initial amount. So our first problem here, you deposit $4,000 in an account that pays 6% annual interest compounded continuously. So how you know to use this PERT formula is if you see the words compounded continuously. Because remember we had that N where if it was compounded annually or compounded bi-monthly or such and such, you'd change how what the number N was. So this is compounded continuously. So we want to write a function to represent the balance A in the account after T years. So we're going to say A equals that principal amount, which is $4,000, times E to the R. This is our R, but remember I still need to write it as a decimal. 0.6 T. So it's actually more simple than the other ones. If we want the balance after 1 year, well, that's just where we let T be 1. So after 1 year, if you type this into your calculator, I got that A was $4,247.35. So now we want to graph this. So we put it into your y equals. Remember we use x instead of t. It does not make sense to graph below 0. So I'm going to graph 0, 1, 2, 3, 4, 5, 6, 7. We go up to 8. So at the 0 year, we're at $4,000. At 1 year, we're at $4,247.30. At 2 years, we are at $4,510. At 3 years, we're at $4,788.90. At 4 years, we're at $5,085. 5 years, we're at $5,399.40. 6 years, we're at $5,733.30. At 7 years, we're at $6,087.80. Then at 8 years, we're at $6,464.30. All right, so graphing these, have our table at 0, we're at this 4,000. At 2 years, I'm sorry, at 1 year, we're at 4,200, so that'd be like about there. At 3 years, 4,700, so we're almost to that 5,000. At 4 years, we're just past 5,000. At 5 years, we're at 5,300. Did I skip something? What did I skip? 4,788 was my 3 year. 4 year. 1, 2. Oops, I skipped something somehow. There we go. Because at 4 years, we're at that 5,000. At 5 years, we're at 5,300, so it's just past that quarter mark. 6 years, we're at 5,700. At 7 years, we are at 6,000, just above 6,000. 8 years, we're at 6,400. So you can see this is an exponential growth. Oops. It's not growing quite that fast. Growing about like that. Alright, so rough estimate. So that's graphing the function, and then it wants us to use that graph to estimate it at 15 years. So at 15 years, I put it right around $9,000. So around $9,000, which of course we can verify on our calculator actually. And 15 years is actually closer to 10,000, so our graph's a little off. But yeah, that's how you're going to graph these. PERT's a pretty nice function. So this is what your worksheet today deals with. Remember, I have office hours again today, so if you have any questions, please hop on and let me know, or just shoot me an email.